Okay, good morning, everyone. Let's jump in right away and continue with mesh current analysis. I wish to complete the theory in the first few minutes, then go with the example problem, and then go into superposition and hopefully finish up that example. But let's see how it goes. May or may not get done with everything today. So, okay, in section 02. Okay, any questions before we begin? Any questions from anyone? Okay. All right. So, actually, let's go back to this screen. We looked at mesh 1, right? We wrote out the equation for mesh 1. We use KVL to generate our equations, and the equations will have voltages in them. The voltages will then be expressed as the product of the mesh current that we chose at the beginning of our analysis. Okay. So in mesh 1, we have I1, mesh 2, I2, and mesh 3, I3. We looked at mesh 1. We have three voltages in there. The voltage source VA, VR2, and VR3. And I did that on the next slide. I don't know why I did that on the next slide. Let me actually. Let's just cut it all out and paste it here. Okay. Okay, so in mesh 1, we have three voltages, VA, VR2, and VR3. You apply KVL with the method that you're comfortable with. You do not have to do this, right? Typically, what you would write is VA minus VR2 minus VR3. It doesn't make a difference. Your equation is exactly the same. Okay, I have minus VA plus VR2 plus VR3. Then you apply Ohm's law to that KVL expression, and you express each voltage in terms of the mesh current. So VR2 is I1 times R2. But because it is in a shared branch, we also have to account for the mesh current that is flowing on the other side of mesh 1. If you take all mesh currents to be in the clockwise direction, then when you apply KVL, you can take I1 as positive and I2 and I3 as negative. Okay, this is where we stopped. So let's take a pause. You reflect on that. Let me know if you have any questions before we go on to mesh 2 and 3. Hey, the most important is the current direction for the mesh, and then which currents are positive, which currents are negative. Yes. 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 The logical, I mean, it flows. The conclusion that I just stated, which is I1 is positive and I2 and I3 are negative, those conclusions come from the fact that the point of entry for the current is plus, right? So if I assume a clockwise direction and I sum up the KVL also in the same direction, then those voltages are positive. However, if you look at I2 and I3, let's take R3 first, okay? So focus on R3. I2 and I1 are both clockwise, with the result being that I2 enters from the bottom. Point of entry is plus, point of exit is minus. This time, when I add the voltage for R3 due to I2, it will be negative. Does that make sense? Two hypothetical currents, I1 and I2. So we can say it will have two hypothetical voltages. Those voltages are not real, just as the mesh currents are not real. So if you sum up those voltages in the same direction, one of them is plus, the other one is minus. Yes. So the question being asked is, why do we have these two on the same side? Again, those voltages are not real. I'm just illustrating that those would be the polarity of the voltages that would occur due to I1 and I2. But again, they are not real. We are just using them for the purposes of analysis. Exactly. So again, the point being made was the current direction. We observe the current direction, and then we account for I3. So that's exactly the same thing. Yes. If our chosen current direction is not clockwise, let's say I2 was counterclockwise and coming from the top, then the voltage drop would be opposite. It would not be I1 minus I3. It would be I1 plus I3. Does everyone see that? Right? So again, the polarities for that voltage drop, I1 minus I3, that comes from the chosen current direction. If your chosen current direction is opposite, then it would not be I1 minus I3. It would be I1 plus I3. And when we get to mesh 2, that would be balanced out because it would be minus I1 minus I3. You'd have a double positive in mesh 1. You'd have a double negative in mesh 2. And that's why your answer will always turn out to be correct. Doesn't matter what your chosen current direction is for the mesh currents. Does that make sense? Okay, then let's get to mesh 2 with the same directions. And when we get to mesh 2, we have a circuit. We have a voltage source. We have a resistor. Another resistor here. Now our voltage source, VB, is shared, but it doesn't make a difference, right? VB is just VB. It's a known quantity. The value of VB will be given to us, will be known to us. So we write out VB, then this is R3, this is R4, and again, my chosen current direction for mesh current I2 is clockwise. I1 is also clockwise, and VB, again, shared with I3. Whether we draw out I3 or not doesn't really matter. It makes no difference to the circuit, for mesh 2 at least. So this is mesh 2. Let me draw out a border between the two. Okay. So what do we see in mesh 2? 3 voltages again. And I will write out, let's say, VB, VR4, and VR3 should sum up to 0. Now I2 is rotating clockwise, so my voltages will have the polarity as indicated. And then when you sum up the voltages, it turns out that all 3 of them will be positive. So VB plus VR4 and plus VR3. Again, the analysis technique, it doesn't consist of much. We are simply applying KVL. KVL is something you've already learned in the past, and you also learned in the beginning, in the first 2 weeks of this class. But the new material is basically the concept of the mesh current and the concept of the node voltages, and how to apply KVL and how to apply KCL. Those are the most important. Okay. So VB would remain as it is. Once I apply Ohm's law, VR4 would simply be I2 times R4, and VR3, and you can see if I'm summing up my voltages in a clockwise direction, now I2 is positive and I1 will be negative. And that's why the equations balance out. So it will be I2 minus I1 times R3 equals 0. Let's take a pause, think over that. Let me know if you have any questions. Any questions? The most important point is it was I1 minus I2 in mesh 1, and then I2 minus I1 in mesh 2. If you understand that, then that's pretty much the entire technique. Yes. Yes, because it is. So the question being asked is, why is it just I2 times R4? Well, R4 is not a shared branch. It only has one mesh current through it. Yeah. So the two currents only appear if the resistor is in a shared branch, and then we have two mesh currents flowing through the same resistor. Then let's look at mesh 3. Let me move this to the side. Okay. M3, we had, what do we have? One voltage source and two resistors, R1, R2, and VB. Okay. So we have R1, we have R2, and we have VB. We have I3 flowing in the clockwise direction. This is R2. R2 has I1 going in the opposite direction. This is plus on the left, minus on the right, plus on the right, minus on the left, as the correct is shown. All right, let's see. R1, R2, 3 VB plus on the left. Okay. Okay, once we take this mesh, we have three voltages again in this mesh. You apply KVL, write out the three voltages. The three voltages are VR2, VR1, and VB should sum up to 0. When I apply again, the technique is different. So I get plus VR2 plus VR1 and minus VB equals to 0. Okay. Or if you use your techniques, you might get VB minus VR1 minus VR2 equals 0. Same equation. Then apply Ohm's law. In VR2, we have I3 as positive, I1 as negative, times R2. R1 is not shared, and because it is not shared, is simply I3 times R1 minus VB equals to 0. All right, think over that. Let me know if you have any questions. Does that make sense? Yes. Question? That is correct. So the question being asked is if instead of VB, if we had a resistor in there, then that would also be shared between mesh 1 and mesh 2. I mean, sorry, mesh 3 and mesh 2. And then that would also be an equation similar to R2. Yeah. But because it's a voltage source, again, VB is a voltage source, even though it is shared, we don't really care about it because we are writing a KVL equation, meaning we are summing up the voltages. So if we already know the value of that voltage, then we don't need to do anything. We simply plug the value in as it is, and that's it. Yes. Yeah, but this is again, this part of a larger circuit. You can simplify, yes, but they have to be in series or in parallel. In this case, None of the resistors are in series or in parallel. If they are, yes, you can. Yeah. No, that is just, so I think the question being asked is, if you look at just a single mesh, can we simplify? The answer is no, because that is just for explanation purposes. I'm just explaining one mesh at a time. So I'm drawing one mesh at a time. The circuit has not changed. That's the answer. Yeah. That's actually a very good point. Okay, so I'm drawing single mesh at a time just for explanation purposes. The circuit is not changing, okay, from the original. Yes. It is arbitrary, yes. So the question being asked is, how do we assume the direction of the current? Well, it's up to you. There's only two choices, either clockwise or counterclockwise. And so you pick and choose, and that's it. It's completely arbitrary. I typically just tend to choose all of them clockwise. That keeps things simple. And that way I can just do I1 minus I3. And yeah, when I get to the next mesh, it becomes I3 minus I1. Okay, move on. All right, let's look at the example then. I think we summarized this last class. Again, if you have any questions, let me know. Okay, the first step is, of course, identifying the meshes and assigning mesh currents to it. Then you write down the KVL. Okay, do not skip that step. Write down all the voltages you have in there so that chances of errors are minimized. And then once you have the voltages, apply Ohm's law and then express each in terms of the mesh currents. Okay, solve for all mesh currents and resistor voltages. That's the question being asked. Voltage sources VA, VB, and VC are given to us. So are the resistor values. Our job is to find all the resistor voltages using mesh current analysis. Okay, so it's not explicitly stated that you use the mesh current analysis technique, but if the question states solve for all mesh currents, that's the technique you have to use. And if I haven't stated it before, I think I have stated this before, probably on the first day of class, but I'll remind you. If a problem in a quiz or in the exam states use a particular method, then you have to use that method. You cannot use anything else. If you do, I would not be able to give credit. The reasoning is we are required to teach you or impart certain knowledge about certain topics. Then we are required to assess your understanding of that certain topic. If you do not show me that particular topic, that particular technique, then I have no basis for judgment, no basis for assessment. So if a problem states solve it using KCL, you have to use KCL. If it says node voltage, you have to use node voltage. Okay, how many meshes do we see? Calculators out. This is not going to be that difficult. How many meshes do we see? Two, right? Meshes are easier to identify. Closed loops that do not have any other loop in it. Then, as usual, I'm going to choose mesh currents with a clockwise direction. And let's see, because there are A, B, C in there, there's I, R1, R1, R3, R4, R4. What I'll do is I will choose this as IX and IY. So I won't use 1, 2 because it might cause confusion between IR1 and IR2. So let's use IX and IY. And then we have VA, VB, and VC. Okay. So let's draw out mesh 1. Mesh 1 comprises of the voltage sources VA and VB. And let's draw it out here. And the resistors R1 and R2. So plus minus VA, plus minus VB, R2, and R1. And I have I1 flowing through mesh 1. Oh, IX. I'm going to stop that. IX. And then I also have IY flowing in that direction. Okay. So how many components? Once you finish drawing, let's take a pause. If it's a current source, we ignore the current source. Current source will come on the next slide. How many voltage sources and how many voltage drops? Total. Voltage sources, 2 resistors. So total voltages in my KVL loop, 4 terms, right? 4 terms. So 4 terms, starting from the bottom left corner, I'm going to write out VA, VR1, then VB, and then VR2 should all sum up to 0. Now again, the way I apply it, VA would be minus, VR1 would be positive, obviously because we are in mesh 1, and my KVL summation is in the same direction as the mesh current. So plus VR1 plus VB plus VR2 equals to 0. Check that equation against your technique. Verify you have the same. So this is KVL, right? We applied KVL here. Now we apply Ohm's law. And then we express each resistor voltage in terms of the mesh currents. Does everyone have the same equation? Okay, nod, shakes. Okay, so what do we have for VR1? Is it in a shared branch? That's the question you should be asking yourself. Is it in a shared branch? No. Then it's simply V equals IR. I is I1. Oh, IX, sorry. IX times R1. VB is the voltage source, so we leave it alone. And then VR2 is VR2 in a shared branch. Okay, VR2 in a shared branch. The answer is yes. R2 is shared between mesh 1 and mesh 2. IX, we are writing the KVL for mesh 1, where IX is positive. So IY is negative because we chose it clockwise. It would simply be IX minus IY times R2 equals to 0. That's our KVL expression. Now we simply enter all the values that are known to us. VA is 10. IX is our variable. R1 is 5. Plus VB is 9 volts. And then R2 times IX. R2 is 10 ohms. So I'm going to write IX times 10 minus IY is IY times 10. So 0. Rearrange the terms and reduce it to the form of AX plus BY equals to C. So I have 15 times IX minus 10 times IY equals to 1. And I will label that as equation 1. Equation 1. Any questions? If you're solving this, do you have the same equation? Just take a pause, go through the steps, see if it makes sense, see if there are any errors in the equation. I gotta make an error once in a while just to see if you guys are paying attention. Yes. Let's see, 5. No, so we have 5 times IX here. and then 10 times Ix there. And then let's see, minus 10 plus 9. So you got minus 1. Minus 1 goes on the other side. You got 1. Yeah. Yeah. No, it's all good. It's all learning, part of learning. How about everyone else? All good? Okay. All right. So then let's go to mesh 2 on the left. Mesh 2. We apply KVL to, this is a slightly bigger circuit. So we have VB, R2, voltage source VC, R4, that comes up to 5 components or 5 voltages. So R2, R4, R3, VB, and VC. And of course, our mesh current, IY, and IX. Oh, sorry. Okay. 3 resistors, 2 voltage sources. Okay. So we have VR2. I'm starting from the bottom left corner. I have 5 voltages, so 5 terms in my equation. Actually, let's wait a few seconds while everyone writes this down. Okay, so once you have your mesh drawn out, count the number of terms in your, count the number of components, and those components, of course, will equal the number of terms in your equation. So here we have 5. Starting from the bottom left corner, I have VR2, VB, VR3, VC, and VR4, summing up to 0. And again, apply your own techniques. Me, this would be plus, minus, plus, minus, plus, minus. And sum up the voltages going in the same direction as my mesh current. So I have VR2 minus VB plus VR3 plus VC plus VR4 equals to 0. Check that against your own KVL expression. Good. Okay, then we apply Ohm's law. What do we have? This is KVL, Ohm's law. VR2 is in a shared branch. VR2 is in a shared branch. So if it's a shared branch, you have 2 currents. You have to account for both. In this case, it would become IY minus IX times R2 minus VB plus IY times R3 plus VC plus IY times R4. Depending on the number of resistors in that mesh, you should have that many currents to add up. That many constants to add up. So IY minus IX times R2. R2 is, what is R2? 10 ohms. So I would have IY times 10 minus Ix times 10. VB is 9 volts, so 9 plus Iy times R3, 5, plus Vc, which is 1 volt, plus Iy times R4. So Iy times 5. Okay, Iy times 5. We have 3 resistors in the circuit. So there should be 3 terms with the variable Iy, right? So you have 10 times Iy, 5 times Iy, and again 5 times Iy. If you don't have those, then your equation would be incorrect. 3 resistors, so you should have 3 terms for Iy. And then 1 shared branch, so that shared branch is with Ix, so 1 term for Ix. You reduce, add up and reduce all the values, you would obtain, let's see, Ix, there's only 1 term, so minus 10 times Ix plus, let's see, 10, 5, 5, 20. 20 times Iy gives me minus 9 plus 1 is minus 8. We take it on the other side, we get plus 8. I'm going to call that as equation 2. Solve this equation on your calculators using any method you choose, and you should have the answer for both. How many of you have MATLAB installed on your phones? Anyone? Do you know how to plug this in? Okay. All right. So again, I mentioned this in the last class. If you wish to go ahead and do this, you can install MATLAB on your smartphones. A very handy way to actually learn. So what you would do is, let's see, you'd put the variables in a matrix. So I'm going to call this A. You write out the constants for Ix and then for Iy. Oh, sorry, for equation 1 and then for equation 2. So the straight brackets. From equation 1, I have 15 times Ix, and then I have minus 10. So in MATLAB, all you're going to do is define a variable. Let's call it A. A equals, A doesn't have anything to do with the VA. Okay, so it's just a random variable. A equals, fixed bracket, 15 times Ix minus 10 times Iy. So enter both the constants with the space in between, and that's it. And then you define equation 2, semicolon, a semicolon, that's not a J, it's a semicolon. And then for equation 2, minus 10 plus 20. That's it. And then you type in B equals your values, which is 1, and again, semicolon 8. And then you press enter after both. And then you define your answer. Let's say our answers we want, let's type in like Z equals A / B, and that should spit out values. Go ahead and enter it. If you have it, enter it, and then I should have written this out. Solving this in MATLAB, just plug it in, and it'll give you the answers for your Ix and Iy as Z. Yes. That's not a J, that's a semicolon. Let me mark it out. Semicolon. And after every line, you press enter. It'll automatically display everything in the matrix. Manually, if you wish to solve these equations, it's not that hard. I have equation 1, I have equation 2. So let's do this. I'm going to take, it's 15 times Ix, 10 times Ix, multiply by 1.5. I can do that. Or I can take equation 1 and multiply it by 2. So take equation 1, multiply by 2. That would give me That would give me 30 times Ix minus 20 times Iy equals to 2. Let's call this equation 3. You do equation 2 plus equation 3. And that should give you, what does it give me? Minus 20 times Ix equals 10. 20 times Ix is 10. Plus 20. Okay. 20 times Ix is equal to 10. Therefore, Ix is equal to 2 amps, 0.5 amps. 0.5 amps. Did anybody plug this in MATLAB? Did you get the same answer? You didn't? I see your shake and I see your nod. Yes? Okay. So Ix is 0.5. You plug Ix into any of the other equations, and you can get Iy as 0.65 amps. And once you have these mesh currents, you can calculate any resistor voltage, right? We wrote out the KVL at the beginning. So when we wrote out KVL, we have each one of these is already done for us. So we can find any resistor voltage. All you have to do is plug in the value of the mesh current in those terms that you see in those equations, and you find those resistor voltages. Once you have the resistor voltages, you can also find the resistor currents if they are shared branches. Does the entire process make sense? Let's take a pause. Let me know if you have any questions. Also, if you have a programmable calculator and you know how to do this, yes. So VB is equal to 10, but when I add up the voltages, I have a negative according to my summation loop. And so that's why it's minus 10. No, VB is equal to 9, yes. VA is 10, VB is 9, and VC is 1. Yeah. But that's good. Actually, speaking up like that, it minimizes chances of your errors when you go forward trying to solve it for quizzes and trying to solve it for final exams. Okay. Again, if you do this in a quiz, or it's better to do it here right now while you're learning rather than to do it in a quiz or a final exam. Okay. Okay. Other questions? All right. Then let's call on super mesh. Like supernode, it is just a technique. If you have a current source, especially in one of the meshes or in a shared mesh, could be anywhere, could be in a shared mesh, could be outside a shared mesh. Okay, so this could just as easily be two current sources. Okay, super mesh is a shortcut. It allows us to apply KVL around a current source. Current source value would be given to us, 1 amp, 2 amps, 3 amps, but we don't know the voltage across that current source, right? So we can't write a KVL expression for that current source. So all we do is we combine two meshes together and we write a KVL around those two meshes. So instead of applying KVL around a mesh, we are applying KVL around a loop that contains both those meshes. Okay, so all we are doing is here, this is Let's try this. M1, M2, and M3, and corresponding mesh currents I1, I2, I3, right? So if you apply KVL in mesh 1 or mesh 2, we cannot do anything with that current source. Again, KVL is summing up the voltages. So we don't have the voltage across the current source. Similar to the node voltage analysis method, this is a shortcut. All we are doing is, instead of applying KVL in individual mesh, instead of applying KVL to individual meshes, you combine both the meshes together, and you apply KVL in the outer loop, ignoring the current source. That is all you are doing. You ignore the current source, you apply KVL in the outer loop. So again, the name sounds fantastical, but the technique is not. It's simply a shortcut. It's a way to apply. Yes. The question being asked is, if there's no loop without a current source, well, if it happens in real life, we would not use this technique. We would just use node voltage analysis. But good question. I mean, if there is a loop that has multiple current sources, this is all like, when we perform theoretical analysis, that is certainly possible. That is certainly possible. We might end up with a current source in a loop, and then, what if there's no way? Then we would solve it using other techniques. Yeah. So this would be M1 plus M2. This is 2 ohms. This is 4 ohms, 1 ohms, and 10 volts. Now, the thing to be careful about is you do not assign a new mesh current. The mesh currents for each resistor remains the same. Meaning, for M1, you still have I1, and for M2, you still have I2. And that's why the term super mesh, because you're not ignoring the two individual meshes. You have to account for the individual mesh and the individual mesh currents. And so when you combine the two meshes together, you still have to account for I1 and I2, as well as I3. Actually, I drew it rather too close to the top. Let's see. We also have I3 from the top. So I'm going to draw it like this. So my equation, my KVL expression, when I apply around this larger loop, I have 4 terms, right? The 1 ohm resistor, the 2 ohm resistor, the 4 ohm resistor, and the 10 volt source should sum up to 0. I1 will be positive, so it'll be I1 times 1. And then, let's see, this would be, I didn't leave enough space. This would be I1 minus I3 times 2 plus I2 minus I3 times 4 plus 10. Let's take a pause while you write it down. Think on that. Let me know if you have any questions. Again, all we are doing is we are applying KVL in the outer loop. We ignore the current source by combining both the meshes together. But even if we do ignore the current source, we still have to take the mesh currents into account. Yes, the question being asked is, does I2 stay in its original mesh? And also follow-up question would be, does I1 also stay in its original mesh? Yes, the answer is correct. The original chosen mesh currents will only affect the components in that mesh. Okay, all we are doing is we're ignoring the current source, but we cannot ignore the chosen assumptions at the beginning. Yes. If there's a current source and we can't, okay, the question being asked is, when should we use this? The answer is when there's a current source and we are unable to write a KVL expression around that current source. If we can solve a circuit without, applying KVL, sometimes we don't need to. Sometimes there are so many meshes in a circuit, so we don't need to write that many equations. We can solve the circuit with like 2 or 3 equations. Then we may not need to write a KVL. But if there's ever a case where you have to write a KVL around a mesh that has a current source, then this is what you would do. You would combine that mesh with another mesh, and the mesh is in a shared branch or not, then you can do that. If that mesh current, if the current source is not shared, if it is not shared between 2 meshes, for instance, something like this. Let's say the current source is not shared. Okay. As an example, again, random circuit. This current source is not shared. I would choose my current for mesh 1 as IX, and I can choose IY. Let's call this IS equals 1 amp. It's not shared, meaning my mesh current, the assumed mesh current flowing through that current source, is the only current that's flowing through that branch. I can write the value for IY directly. What is the value for IY? -1. That's it. -1. So IY will be equal to minus, well, actually, it will be minus IS, and hence it has a value of -1 amp. So you automatically have an answer for one of the mesh currents. Then you only need to write one more equation in the other branch, and that's it. Also, when a current source is in a shared branch, I can express the current source as a result of the 2 mesh currents. So if I go here, how can I describe this 5 amp source in terms of I1 and I2? Which mesh current is flowing in the same direction? I2, which is in the opposite direction. So I2 minus I1 is equal to 5 amps. That is an extra equation we can write. And that allows us to actually plug in the value. So we can express I2 in terms of I1, right? I can write I2 is equal to 5 plus I1, or I can express I1 in terms of I2. I can write I1 is I2 minus 5. And then wherever I have my equations, any equation I have I2 or I1, I can substitute or plug the other one and reduce it. Then I have eliminated one unknown variable. Okay. Think on that. And then next class, if you have any questions, please feel free to bring those up. So we'll end here today. The measurement analysis homework is due tomorrow night. There's only 3 problems. It's plenty of time to get that done. I will post some hints like the previous one. After 12 o'clock, I'll create a PDF and I'll post it online. So everybody can take a look at that. All right, I'll have a good day and I'll see you all on Friday.